All right, so let's look at our next concept, and that is the concept of pH. And what pH is to give us a more understandable scale to look at acid and base concentrations. And the first question you might have is now, why is that at all necessary? And what I'll do is I'm going to try and give you a brief overview here. And if you might recall that you've looked at before, is an acid or a base, meaning is its concentration, or how it's defined, is something to do with an hydronium ion concentration. So if you look, if it once an acid dissociates, so you have some sort of acid, hydrochloric acid or acetic acid or something, it will have an hydronium ion concentration. And these numbers often differ by quite a couple of orders of magnitude. So, if you write these out, for example, for a weak acid like acetic acid, it's 1.6 times 10 to the negative 3. So this is acetic acid. Another number for rainwater is 2.5 times 10 to the negative 6 molar. So it's rainwater. And this can be quite cumbersome to write out, right? And I mean, it looks nice to write it out in scientific notation, but there's a nice convenient way to express something when you have it expressed in terms of something to the power 10 to the power something. And that is to use what we call a base 10 logarithmic scale, or just a logarithmic scale. So that is where this definition of pH comes in. So we call it the negative of base 10 logarithm of the hydronium ion concentration. We define that as the number pH. So that then means if you take log minus log of this number here, then you get a very nice number. So for example, if you take minus the log of 1.6, so if you take pH, calculate the pH here, so minus log of 1.6 times 10 to the negative 3, you're going to get a simple number. Let's call it a simple number. You're going to get something like 2.80. All right? And that's much nicer to look at, or it's much more interpretable, because in a broader sense, how we've gone ahead and defined the pH scale is when numbers are close to 0, you get acids, something is acidic, and when it gets closer to 18, something becomes basic, right? And when it's 7, then you have something that is neutral. So that is how we define it. So this is basically a way to look at your hydronium ion concentration, convert it to a more digestible number, if you were to call it like that, so meaning a number between 0 and 14. Sometimes it goes into the negative, sometimes it goes higher, but a number that you can clearly look at and you can know whether or not something is acidic and basic, because it's very difficult to tell whether or not these things are actually acidic or basic looking at the hydronium ion concentration, right? These numbers are difficult to look at. These numbers, however, give you a very clear indication whether or not something is acidic or basic. All right. So it gives us a very common way to look at all sorts of, or at acids and bases. In other words, a scale. All right. Something else that you can then do with that is if you take the inverse, so in other words, if you take the antilog, so in other words, 10 to the minus pH, so you take literally this number, and you say 10 to the power minus that number, that will then tell you what the concentration is of the hydronium ions in that solution. So that is what we call the antilog for a specific solution. All right, so those are the things that I wanted to introduce here. So let's look at how we can put that into practice. So yeah, so that's our next thing. Right, so this question, some three examples for us to look at. So it says, consider the following questions. It says lemon juice has a concentration of hydronium equal to some concentration. What is its pH? So this one is a straightforward situation where you're given the concentration and you're asked to calculate the pH. Right, so all you have to do is to say, well, pH is going to be equal to negative the log of the hydronium ion concentration as given. And that means we take negative log of 0.0032, all right, and that's going to give us a value of 2.49. All right, notice how I rounded this to 2 decimal places. We'll speak about that just now, and not two what you might call significant figures, but 2 decimal places in this case, because the significant figures for logs work slightly different. All right, so that's our pH. And you notice that's acidic, because lemon juice is acidic. What a shock. All right, so B. It says seawater has a pH of 8.07. What is the hydronium ion concentration of this solution? All right, so this one is just the opposite. So here we can take the antilog to give us the hydronium ion concentration, because here we just asked the question in reverse. So we want hydronium ion concentration. We're given pH. So we'll use this. So it means 10 to the negative 8.07. Put that into your calculator, and you should find 8.5 times 10 to the negative 9 molar. And notice now, it's two significant figures, and once again, why? Once again, we'll talk about that just now. Right. Then in the C part, we have a solution of nitric acid, has a concentration of 0.056 mole per liter. So molar, what is the pH of the solution? So we're asked the pH, but we're given the concentration of the acid. So we have to do some thinking here. So our first part is to recognize maybe what the acid is. So this is HNO3. That is nitric acid. And if you recall your weak and strong acids, you'll recall that this is indeed a strong acid. So nitric acid should fully ionize. So that will fully ionize with water, and that would then form hydronium aqueous plus NO3 minus aqueous. All right. And notice, or important note here, like I said, it's a strong acid, so we get 100% or fully ionized. Ionize. All right, 100% ionization, which basically just means it will give, for every 1 mole of this, 1 mole of hydronium will form. So in other words, if this thing's concentration is 0.0056, the hydronium ion concentration must be the same. That's what it is implying about strong acids. If it were a weak acid, there would be it would be a bit more involved, and that falls outside the scope of this specific course. So strong acids fully ionize, and hence we can do this one-to-one relationship. The concentration of the acid will be equal to the concentration of the hydronium. So in this case, the concentration of our concentration of HNO3 is going to be equal to the concentration of NO3 minus, right? It's going to be equal to the concentration of H3O plus, because we get 100% ionization. And that is given in the question as 0.0056 molar. Okay, because it's a strong monoprotic acid. If it was a diprotic acid, then of course your stoichiometry would change, but you can just remind yourself of how those ones work. All right, so we're asked for the pH of the solution. So what is this? pH, of course, then equal to minus the log of concentration of hydronium. So that means minus log of 0.0056. That is equal to 2.25. Notice again, 2 decimal places. Okay, so let's quickly talk about how the rounding here works. So this is a comment in general about logarithms and significant figures. So notice each time here how many significant figures we were given. So let's first talk about A and B. So you would call this two significant figures, right? 0.0032 and 0.0056. And notice in our answers for both of those, we had three numbers, 3 digits. Why is that? Well, for logarithms, how they work, so maybe I can just do this off to the side. So logarithm, how do you spell this word? Logarithms, significant figures. All right. The textbook also gives this in the appendix, which I gave in the notes. The logarithms, how they work is it's split up into 2 sections. So if you have, for example, something that if you've calculated it, if you've taken minus log of 3.2 times 10 to the negative minus 3, right? And you now get the answer 2.49. You would typically then ask yourself, right, how would I need to round this? You would want to say maybe 2.50. But the answer lies in how logarithms are defined. The first number, so the number on this side, is called the characteristic. This is just some interesting information. And then the number to the right, this one is called the mantissa. And interestingly enough, how logarithms work is you look from here to count your significant figures. So you count then 1, 2 significant figures, and that is how you round. Okay, so you see here 1, 2 significant figures, and you go 1, 2 significant figures from the mantissa is how you count. All right. So in a similar fashion, for B, you notice how we went 10 to the power minus pH, and then we said 10 to the minus 8.07, and then we gave an answer as 8.5 times 10 to the negative 9. Why? Because it is technically, it's a pH. So how many significant figures is that pH given as? It's not 3 because the 8 does not count. It's the 0 and the 7. So that means the answer will be rounded to 8.5, which is 2. Okay. That's how significant figures work in pH context. So maybe you can just remind it's when you're working with pH. So you look after the decimal point. When you have log equals something, you count after the decimal point. If you have 10 to the power, you count after the decimal point to see how many significant figures you must produce your hydronium ion concentration. Okay. If you need more information about this, Appendix A can be very useful to remind yourself of that. But also, once you get used to the working with pH, it should be fine. All right. I hope this was insightful as always. All right. Thank you for watching.